This is week 7 of Engineering Thermodynamics course online session. Uh, Till previous week we saw how to solve in closed system, how to solve first law uh, analysis for this closed system. So there we considered a system where there is no mass transfer or any fluid which is coming in or going out. So we have fixed mass in the system, and there were heat transfer and work transfers. So interaction between those and how that influenced the internal energy. So that's what we mainly looked at and solved problems regarding those. So evaluating one of the energies or the work or heat. In open system, which we'll be seeing today, and to an extent an unsteady analysis of an open system. So that's what we'll be looking at in problems regarding those in this session today. So in an open system, what happens is now it's not constrained anymore on the mass transfer. So you have mass transfer and along with heat and work transfers. So the energy balance now is you have energy coming in and energy going out, and some energy can be stored in the system. So if the energy if it's a steady state system such that at any point of time, so variation in time, if you see there is no change in the properties, so that's a steady state. So in a steady state system, so energy coming in will always be equal to energy going out. So in the system there is no accumulation of this energy or the change in energy of the or the properties of the system. So that will remain same with respect to of time. So that is your steady state. In an unsteady state, what happens is there's something coming in energy and there's something going out, but the energy of the system itself changes. So to give a simple example is opening a uh, um, compressed air cylinder. So here the gas will escape. So there is a energy and mass which is going out. So with respect to time, the cylinder is getting emptied. So both energy and the mass of the system is reducing. So that is an example of an unsteady system. So regarding those, we'll see how to solve this. So we'll start with simpler problems on applying this steady flow energy equation, which we apply an extension okay, the first law to an open system. So similarly here you have this change in enthalpy instead of internal energy, and same potential and kinetic energy changes is equals to your heat and work transfer. That is your steady flow energy equation. So in an open system you had internal energies. Here we deal with enthalpies. So we'll start with simple components and steady flow cases, and apply a steady flow energy equation to these components and see and evaluate how these components behave. So the first case is with a nozzle. So the question is, a nozzle receives an ideal gas flow with a velocity of 25 meters per second, and the exit is at 100 kilopascal and 300 Kelvin with a velocity of 250 meters per second. So determine the inlet temperature if the gas is argon, helium or nitrogen. So what is given is you have a nozzle and the inlet velocity is given, exit velocity is given, and the exit pressure and temperature is given. So we need to find out what is the inlet temperature. So first is, so we take control volume across this nozzle. So we have mass balance and energy balance can be done. So the mass balance gives whatever mass which is coming in, it goes out. So there is no accumulation of mass. And here what we assume is the nozzle is adiabatic, so there is no heat transfer, and in nozzle the nozzle doesn't generate any work, so your work transfer will also be 0. So if you apply steady flow energy equation, so you get enthalpy plus your kinetic energy uh, plus Q equals to enthalpy exit plus W and kinetic energy and so on. So work and heat transfer will be 0. So what you get is HI, which is the enthalpy which is coming in of the fluid, plus half VI square. So that's the kinetic energy divided by mass specific energy. So equals half velocity exit square plus enthalpy at the exit. So if you rearrange it, we get HI is the inlet enthalpy equals HE plus half VE square minus half VI square. So we can write the change in enthalpy to be now half of the difference in velocity squares of exit and inlet. So Cp Ti minus Te, which is the change in enthalpy, equals half VE square minus VI square. So what get is V, we know it is 250 and VI is 25 meters per second. So substituting the values, we get Cp Ti minus Te to be 30.938 kilojoule per kg. So now what is asked is we need to find out the inlet temperature. What should be the inlet temperature for the gases argon, helium and nitrogen. So for argon, your Cp value is 0.52 kilojoule per kg Kelvin. So just substituting there, we get delta T to be 59.5 for argon. So Ti is 359.5 Kelvin. Similarly for helium, here Cp is 30.938 divided by 5.193, which gives you 5.93. So your inlet temperature is 306. And similarly for nitrogen, Cp is 1.042. So the inlet temperature comes out to be 330. So next is we have a liquid water at 180 degrees Celsius and 2000 kilopascal is throttled into a flash evaporator chamber having a pressure of 500 kilopascal. So neglect any change in kinetic energy. What is the fraction of liquid and vapor in the chamber? So we have liquid water which is coming in, and that you're putting it into a flash evaporator. So where this is the pressure is reduced to 500 kilopascal, and it gets converted into your liquid and vapor. So we need to find out what is this fraction of liquid and vapor which is generated in the flash evaporator. So similarly, applying energy equation here, since this is across a valve, what we'll have, because you have to reduce pressure from 2000 kilopascal to 500 kilopascal, so it will be across a valve. So what we assume is across the valve there is no heat transfer and there is no work transfer. So what we get is the enthalpy, the total energy at state 1 equals to state 2. So we have enthalpy, potential energy and kinetic energy. If we assume the velocities are same, nearly the same at inlet and exit, so you can neglect the kinetic energy and also the potential energy, because the valve there is no much difference in height, so can neglect the potential energy as well. So what we get is the enthalpy at exit is equal to enthalpy at the inlet. So from the table or steam table, what we get is for 2000 kilopascal and 180 degrees Celsius, we find out the enthalpy to be 763.71 kilojoule per kg. So for corresponding to this enthalpy and a pressure of 500 kilopascal, that is our state in the flash evaporator. So this lies in a two-phase case. So H2 will be now can be written as the enthalpy of saturated liquid plus the quality times the change the latent heat, the enthalpy of saturated vapor minus saturated liquid enthalpy. So you get H2 is equals to HF plus X2 HFG. So we can find out the quality. So quality comes out to be 763.71 is your enthalpy. So minus 640.21 is your saturated liquid enthalpy divided by your latent heat, which is 2108.47. This is corresponding to pressure of 500 kilopascal. So your X2 is 0.0586. So that says 5.86% is vapor and the rest 94.1% is liquid. So moving on, the next question is a small high-speed turbine operating on compressed air produces a power output of 100 watts. The inlet state is 400 kilopascal and 50 degrees Celsius, and the exit state is 150 kilopascal and minus 30 degrees Celsius. Assuming the velocities to be low and the process to be adiabatic, find the required mass flow rate of air through the turbine. So what we have is a small high-speed turbine operating on compressed air produces a power of 100 watts. So the power produced by the turbine is given. They have given the inlet state is 400 kilopascal and 50 degrees Celsius, and they have said that the exit state is 150 kilopascal and minus 30 degrees Celsius. So both inlet and outlet is given. What we need to find out is what is the required mass flow rate that of the air to be given to the turbine to generate this condition. So we'll see this example. Where can you find this? So peculiar, you have a small turbine with 100 watts. So these are generally used in by dentists. So if you go for a dental checkup or something, so to drill the teeth for doing a root canal or to get rid of the plaques and so on, to trim the tooth and so on, they'll use a drill. So this drill, you cannot put any pass any electric current inside, so that will harm the patient. So what generally is used is you have a drill, and the other end of the drill you have a turbine, and a compressed air is passed. So this compressed air drives the turbine, and that turbine will drive the drill. So you get you can then you use a drilling operation can be done. So these are kind of turbines which are used there. So small turbines. So this is an example of that. So you apply a control volume across this turbine. So what you have is an inlet and exit fluid which is coming in at some internal enthalpy. If you assume the kinetic energy and potential energy is negligible, so your inlet enthalpy equals your exit enthalpy plus the work which is being transmitted from the turbine. Since the heat transfer is 0, so Q we get to be 0. So what we get is H in, which is the inlet enthalpy, equals to the enthalpy at exit plus the work generated in the turbine. So we assume air to be an ideal gas. So H in minus H out, we can assume it to be Cp delta T. So Cp of air is 1.004, and we know the inlet and outlet temperatures. So multiplying by the temperature difference, which is 80, what we get is W to be 80.3 kilojoule per kg. So that is a specific work which is generated, but we know the actual work which is being generated by the turbine to be 100 watts. So that divided by the specific work should give us the mass flow rate which is required. So W is 0.1 kilowatt divided by 80.3 kilojoule per kg gives us 0.0125 kg per second or 1.25 grams per second. So that's the amount of mass flow rate which is required to drive this turbine to generate 100 watts of energy or work. So in the first case, and the first and second cases, what happened is in the nozzle, what happened is the both heat transfer and work transfer were 0. So there was no heat and work interaction. So but the kinetic energy was getting changed. So the whatever in enthalpy is the energy of processed by the fluid. So this is getting converted into velocity. So there was a change in energy from the enthalpy to a kinetic energy. So this was getting balanced. The second case of valve, what happened is except enthalpy, rest everything was negligible. So kinetic energy and potential energy were negligible. There was no heat transfer and there were no work transfer. So only thing which was getting balanced is the enthalpies. So in the valve, your inlet and outlet enthalpies will be same. So that's why it will be an isenthalpic process. So enthalpy will be constant. So that is called an isenthalpic process. So your enthalpies will be constant across the valve. And then in this case, in compressor and turbines, so what we assume is ideally we want heat transfer to be 0, but there are cases this is process to be an adiabatic process, but there are cases where you will have heat transfer as well. So you can have heat transfer as well. So here we assume that kinetic energy and potential energy are 0. So whatever enthalpy change is there, so that change is what drives your work, or the other way around. In turbine, you get positive work out. In a compressor, it consumes work, and that that work is in getting converted to and increasing the enthalpy of the fluid. So that's what happens in an compressor. So, and in a heat exchanger, what happens is there is only heat transfer. So this enthalpy, just like here in an ideal adiabatic compressor and turbine, where there is no heat transfer, you have just interplay between enthalpy and work. In a heat exchanger, it is just interplay between enthalpy and heat transfer, and there is no work in heat exchanger. So this is an example of an heat exchanger. So a chiller cools liquid water for air conditioning purpose. Assume 2.5 kilograms per second of water at 20 degrees Celsius and a pressure of 100 kilopascal is cooled to 5 degrees Celsius in a chiller. How much heat transfer in kilowatt is needed? So you have water which is in a heat exchanger which is coming in at 20 degrees Celsius and 100 kilopascal and going out at 5 degrees Celsius. In the process, it is rejecting heat. So this is the scenario. If you put a control volume, so there is a water which is coming in at 20 degrees Celsius and 100 kilopascal, and ideally assuming there is no pressure losses, so the exit will be 5 degrees Celsius and 100 kilopascal, and there is a heat transfer, so there is no work transfer, 0, and we can assume kinetic energy and potential energies are negligible. So if you apply the energy balance here, so energy coming in HI, and then Q is going out, and A equals HE. So you get Q out is HI minus HE. So from the table, you can find out HI and HE. You get HI to be 83.94 kilojoule per kg and HE to be 28.98 kilojoule per kg. So Q out comes out to be 62.96 kilojoule per kg. So the total heat transfer is mass times the specific heat transfer. So we know mass is 2.5 kg per second. So 2.5 times 62.96 gives you 157.4 kilowatts. So that is the amount of heat which is getting transferred. So if you assume that instead of going finding out enthalpies, if you assume that the specific heat doesn't vary with respect to temperature, so in that case you can write Hi to be Hg minus Hi. So the change in enthalpy equals to Cp delta T. So we know the inlet and exit in temperature, and Cp of water is 4.18. So what you get is 62.7, which if you see it is pretty close to what we estimated using the enthalpy. We got 62.96 using enthalpy. Here we are getting 62.7. And similarly, if you count, if you estimate the total Q heat transfer, it comes out to be 156.75. So next, we have a 500 liter insulated tank which contains air at 40 degrees Celsius and 2 megapascal. So valve on the tank is opened and air escapes until half the original mass is gone, at which point the valve is closed. So what is the pressure inside then? So what is this? We have a 500 liter tank which is insulated, so there is no heat transfer. We know the quantity of volume the tank can contain, which is 500 liter, and the condition at which it has the gas is given to be 40 degrees Celsius and 2 megapascal. So that is the initial condition which is given. Now what is happening is, at the top of the valve there is a top of the tank there is a valve which is being opened, and because of which air is escaping, and once the cylinder is half empty, valve is being closed at that point. So what will be the pressure inside when half of the mass has escaped? So we'll see how to solve this. So first, this is being air, we can assume it to be an ideal gas. So we'll apply ideal gas equation. So you get PV equals to MRT. So the first case we know the pressure, temperature and volume, and for air we also can know your gas constant. So M equals P1 by P1V by RT1. So pressure is given as 2 megapascal. So 2 is 2000 kilopascal multiplied by 0.5, so 500 liters. So 1 liter is 10 power minus 3 meter cube. So you get 0.5 meter cube. Divide by R is 0.287 kilojoule per kg. So that and bar kilopascal 1000 will get cancelled out, and multiply by temperature, which is 313.2 Kelvin. Here it is 40, so 273.2 or 15 plus 40. So that gives you a mass of 11.125 kgs. So initially the cylinder, 500 liter cylinder at pressure of 2 megapascal and temperature of 40 degrees Celsius contained 11.125 kilograms of air. So now what we'll do is the amount of mass, we'll do a mass balance across the control volume, or which is the cylinder. So mass which is there is no mass which is coming in, but there is some mass which has escaped. So that is the initial mass minus the final mass. So the final mass we know is half of the initial mass. So the mass which has escaped is also the same. So that is equal to 5.5625. So the mass which has exited the cylinder is equal to the mass which is present inside the cylinder, because half is being emptied. So half will remain in the cylinder. So that is equal to 5.5625 kilograms. So if you apply energy balance, so you get the energy change in the system equals the energy coming in plus heat transfer and work transfer minus the energy going out. So the change in internal energy of the system is du by dt. So m2 u2 minus m1 u1. So the final internal energy minus the initial internal energy. So that's what we are getting at the left hand side, which is equal to, so there is no energy which is coming in, there is no work transfer, there is no heat transfer, so everything is 0. So there is only a stream which is going out, so that is equals to minus ME HE average. So from here what we can write is the enthalpy average of the stream which is going out is Cp T1 plus T2 by 2 . So what we get here is substituting the values here, so we can get T2 to be 239.4 Kelvin. So P2 will be applying ideal gas equation, we get Mr T2 by V. So mass is, we know, 5.5625 inside the cylinder, R is again 0.287, T2 is 239.4 and V is 0.5 liters. So that gives you 764 kilopascal. So the pressure inside the cylinder will be 764 kilopascal. So what we did is we then applied an unsteady steady flow energy unsteady flow equation for open system. So change in internal energy equals the energy in minus energy out, and change in internal energy is nothing but it's the initial minus the final minus initial. The final is mass times the specific internal energy at state 2, which is minus the initial mass into the initial specific internal energy, equals the mass exiting minus the enthalpy. Since throughout the process where the gas is exiting, your temperature is varying. So what we did is we took an average ideal gas. So we took an average temperature and assumed that the enthalpy to be a function of this average temperature. So we used average temperature as the initial minus initial and final by 2. So that is an average temperature. So HE average to be in Cp T1 plus T2 by 2. And we substituted this in the above equation. So M2 and ME are functions of M1, which is M1 by 2, and U2 is a function of T2, HE average is a function of T2, so the only average is T2. So we estimated temperature at state 2. So using that, we know now what will be the temperature of the content of the air which is contained in the cylinder. So using that and the masses which you know and the volume which we know, we can estimate the pressure. Using that, we have estimated the pressure to be 764 kilopascal. So next question. So refrigerant R134A is compressed steadily in a compressor from 140 kilopascal and minus 10 degrees Celsius to 700 kilopascal and 120 degrees Celsius. The volumetric flow rate at the inlet is 0.06 meter cube per minute. If the heat loss to the ambient is 7% of the input power, determine the power required, and kinetic energy and potential energy changes may be neglected. So in this case, this is not an adiabatic compressor, but there is both heat transfer and work transfer, and they say that heat is lost to the ambient, which is 7% of the input power. So that is given as a function of the work. So whatever amount of work is given, so out of which 7% is lost as heat and rest is going to raising the enthalpy of the refrigerant. And the refrigerant also is given, inlet and outlet conditions are given, saying that the inlet is at 140 kilopascal and minus 10 degrees Celsius, and the exit is at 700 kilopascal and 120 degrees Celsius. So if you write a steady flow energy equation, neglecting the kinetic energy and potential energy, so this is what we get. So the enthalpy exit equals plus the work which is going out equals the heat lost plus the energy which is coming in. So this is what we get. So Q minus W plus M H1 minus H2 equals 0, and what we know is Q is 7% of the input power, and the mass flow rate is not directly given, but a volumetric flow rate is given. So, and that is 0.06 meter cube per minute. So using density or specific volume, we can estimate the mass flow rate. So at the inlet, for a pressure of 140 kilopascal and minus 10 degrees Celsius, from the table in chart of R134A, the specific volume is 0.1461 meter cube per kg, and the enthalpy corresponding to this pressure and temperature is 246.4 kilojoule per kg, and at the discharge of the compressor, which is 700 kilopascal and 120 degrees Celsius, your enthalpy is 358.9 kilojoule per kg. So the mass flow rate now can be calculated. So specific volume flow rate divided by specific volume. So 0.06 divided by specific volume gives you 0.4107 kg per minute. So that is the mass flow rate. So substituting in the above expression, so Q is 7% of work input. So you get minus 0.07 times work plus your work input plus your mass flow rate into the change in enthalpy. So that gives you work to be 49.68 kilojoule per minute. So here the power is negative, which is the consumed by the compressor. So this is what we get, 49.68 kilojoule per minute. So we have an electronic component of a computer which is cooled by air flowing through a fan mounted at the inlet of the electronics enclosure. So at steady state, air enters at 20 degrees Celsius and 1 atmosphere. So for noise control, the velocity of the entering air cannot exceed 1.3 meters per second. For temperature control, the temperature of the air at the exit cannot exceed 32 degrees Celsius. So the electronic components and fan receive respectively 80 watts and 18 watts of electric power. So determine the smallest fan inlet area in centimeter square, for which the limits on the entering air velocity and the exit air temperature are met. So Cp is 1.005 kilojoule per kg Kelvin. So what we have is an electronic component of a computer, just like your processor and motherboard and so on, where you have a fan mounted about it. So a similar idea here. So you have an electronic component which is cooled by air. So you have a fan, and the air is coming in at 20 degrees Celsius and 1 atmosphere. So your atmospheric condition, and the velocity of the air cannot exceed 1.3 meters per second. So that is the limit which has been set by the noise which the air generates, sorry, the fan generates. So if it exceeds 1.3 meters per second, the noise generated by the fan will be more, which you don't want. So you are limiting the maximum flow rate, the maximum velocity of air to be 1.3 meters per second. For temperature control, the temperature of the air at the exit cannot exceed 32 degrees Celsius. So what this says is there should be sufficient air such that the component is getting cooled and the exit temperature does not exceed 32 degrees Celsius. So if you reduce this velocity of air, so you are getting less air and the temperature at the exit will be more, which you don't want. So you are trying to have a higher velocity, at the same time make sure that the temperature at the exit does not go above 32 degrees Celsius. So the electronic components and the fan receive respectively 80 watts and 18 watts of electric power. So 80 watts is generated as heat. So whatever power is going to the electronic component is now is generated as heat. So and 18 watts of power for the fan. So determine the smallest fan inlet area in centimeter square, for which the limits on the entering air velocity and exit air temperatures are met. So we need to find out the area of this fan. So how we can do is, we know velocity. So area into velocity gives you the volume flow rate. So volume flow rate is equals to your mass into specific volume. So that's what is given. So area is mass into specific volume divided by the velocity, and applying the steady flow energy equation here. So what we get is Q heat transfer in the control volume minus the work transfer equals the enthalpy in minus enthalpy out, neglecting the kinetic energy and potential energy. So here there is no heat transfer, there is only 80 watts of electrical energy which is coming in, which is work, and then 18 watts of again power for compressor, sorry, fan. So you have two work interactions. So the total work interaction will be, both are consumed by the control volume, the electronic component and fan, both are electric power which is getting consumed. So there is a work, negative work. So sum of minus 80 and 18 gives you minus 98 watts is the amount of work which is getting consumed. So that is equals to the enthalpy in minus enthalpy out. So mass flow rate comes out to be the work done divided by Cp delta T, and area mass flow rate now can be written as so substituting in the first expression for area. So area is 1 by velocity times the mass flow rate into RT by P for finding out specific volume. So if you see here in the expression, when V increases or T2 decreases, similarly so that's what, if you for a fixed area, if you see, so V and T are proportional. So if your velocity is increasing, your temperature difference will decrease. So similarly, if velocity is reduced, your temperature difference will increase, and respectively temperature T2 will increase because T1 is fixed. So to reduce T2, you need to increase velocity. So the limiting case when we are checking velocity to be at 1.3 meters per second. This is the maximum velocity which you can go. The velocity should be less than, we'll assume velocity is 1.3 meters per second, and T2 should be of 32 degrees Celsius. So to satisfy both conditions, if you put velocity as 1.3 and T2 as 32 degrees Celsius, what we get is area 1 should be greater than 52 centimeter square. So if the area is more than this, for the same mass flow rate, you will get lower velocity. So the minimum area which you require is 52 centimeter square for a velocity of 1.3 meters per second. If you want to operate it at lower speed, then you have to go with a higher area for the temperature to not exceed 32 degrees Celsius. If you're operating the same area and at lower speed, then your temperature will increase. So that's what this expression says. So this gives you the minimum area. So that's what has been asked. Determine the smallest fan inlet area. So the smallest area is obtained when your velocity is at maximum, and similarly the temperature is at 32 degrees Celsius. So that both satisfies, and that gives you the minimum area. You can say area is inversely proportional to the value velocity and the temperature difference. So temperature difference is maximum, then area is minimum. Similarly, the velocity is maximum, the area is minimum. You want the maximum of both. So you taken the velocity, the maximum velocity of 1.3, and similarly the maximum temperature difference which you can have is when your exit is at 32 degrees Celsius. You should not exceed 32, so that is the limiting case. So that will give you the maximum temperature difference between inlet and exit. So inlet is at 293 and exit is 305. So that gives you the maximum delta T which you can have across the electronic component. So both are the maximum values which we have taken, which will give you the minimum area possible. So next question. A steam enters a converging diverging nozzle operating at steady state with P1 equals 40 bar and temperature 1 equals 400 degrees Celsius and a velocity of 10 meters per second. The steady flow through the nozzle with negligible heat transfer and no significant change in potential energy. At the exit, P2 equals 15 bar and the velocity is 665 meters per second. The mass flow rate is 2 kg per second. Determine the exit area of the nozzle in meters square. So what is this? We have a converging diverging nozzle. So in a converging diverging nozzle, your area first reduces and then increases. So this will increase your velocity significantly. In the conditions where the velocity increases and so on, it will be in the advanced courses. But for now, we'll just take what is the velocities which is given and try to apply energy balance over this nozzle. So we have a converging diverging nozzle, and we need to find out the exit area of the nozzle. So what is given is the inlet is given. Inlet is at 40 bar, 400 degrees Celsius, and velocity of 10 meters per second. Similarly, the exit is given as 15 bar and velocity 665 meters per second, and the mass flow rate is also given. So First, applying in mass flow rate will be at the inlet and exit will be equal by mass balance, because there is no accumulation of mass inside the nozzle. Whatever is coming in will go out. So mass at inlet is equals to mass of outlet, and then the second is the energy balance. So the area at exit is mass into P2 by specific volume at state 2 divided by the velocity at state 2. So applying in steady flow energy equation, what we get is m dot is h1 minus h2 plus v1 square minus v2 square divided by 2 plus the potential energy and kinetic energy. So we can neglect the potential energy term. So what we get is h2 is h1 plus v1 square minus v2 square by 2. So why we are doing is we need to find out the temperature, the exit pressure and velocity is given. So here from here mass flow rate, we know mass flow rate, we know velocity. What we don't know is the specific volume. So if we assume ideal gas, we know pressure, we know for air we can know, for steam we can estimate the R. So the only thing which we don't know is the temperature. Or using a steam table with respect to pressure and temperature we can estimate the specific volume. So we need to find out temperature, and that temperature comes from the steady flow energy equation. So applying the steady flow energy equation, we get the enthalpy at exit to be equals to enthalpy at inlet plus the specific kinetic energy difference, which is the v1 square minus v2 square by 2. So we know the enthalpy at inlet can be found out for pressure of 40 bar and temperature of 400 degrees Celsius from the steam table. The enthalpy comes out to be 3213.6 kilojoule per kg, and similarly V1 and V2 are given. So substituting this in the expression here, we can estimate H2. So once we know enthalpy and the pressure, we can estimate specific volume. So enthalpy comes out to be 3213.6, which is the inlet enthalpy, plus your exit velocity is 10 meters per second. So 10 square minus inlet is 10, exit is 665. So divide by 2 and divide by 1000 to convert this to kilojoule. So that gives you the exit enthalpy to be 2992.5 kilojoule per kg. So for a condition of pressure of 15 bar and enthalpy of 2992.5 kilojoule per kg, the specific volume comes out to be 0.1627 meter cube per kg. So therefore substituting this in the expression for area, so A2 is 2 kg is the mass flow rate multiplied by specific volume, which will give you the volume flow rate, divided by your velocity. So that comes out to be 4.89 into 10 power minus 4 meter square. So that is the area which is required to achieve the given condition. This is again in a nozzle, similar to what we did in the previous case, but we have applied to a steam. So we got to use of enthalpy from the steam table. Instead of using Cp delta T, we used enthalpies from the steam table and estimated specific volume, and then found out what will the area of the nozzle to be. So moving on, the next question, a proposal is made to use a geothermal supply of hot water to operate a steam turbine as shown in figure. The high pressure water at 1.5 megapascal and 180 degrees Celsius is throttled into a flash evaporator chamber which forms liquid and vapor at a lower pressure of 400 kilopascal. The liquid is discarded while saturated vapor feeds the turbine and exits at 10 kilopascal with a 90% quality. If the turbine should produce 1 megawatt, find the required mass flow rate of hot geothermal water in kilograms per hour. So what is given is you have a geothermal supply of hot water. So what it says is you have hot water. So geothermal is underground water where it's getting heated up. So you have that supply, and you are using this to drive a steam turbine and generate work. So you have this hot water which is coming in at high pressure of 1.5 megapascal, and your temperature is 180 degrees Celsius. That you are passing it through a valve to a flash evaporator. So now the pressure is reduced to 400 kilopascal from 1.5 megapascal, and that because of this flashing you have both vapor and liquid, and this saturated liquid is now taken out from the flash evaporator and it is discarded, and then only the vapor, saturated vapor which is generated, is passed to the turbine, and that is driving the turbine and exiting at a pressure of 10 kilopascal, and the quality at that point is 90%. We know the turbine is generating 1 megawatt. So to generate that 1 megawatt, what is the mass flow rate which is required of the geothermal water? So at 1, so what is the mass flow rate of water at state 1? So let's see how to solve this. So this the 2 point problems which we see at the start, so combined together. So first we'll consider the flash evaporator. So here, since it's across a valve, we know that enthalpy will be remaining constant at the inlet and exit. So H1 is H1 is at the inlet is for 180 degrees Celsius and 1.5 megapascal, where enthalpy is 763.5 kilojoule per kg. So at this point H1 is 604.74 plus quality into then latent heat. So X comes out to be 0.07439 is the mass flow rate of M2 divided by M1. So that is the mass flow rate. So you get 7.4% of saturated vapor. So H2 is 2738.6, this is saturated vapor enthalpy at 400 kilopascal. So H3 at the exit of the turbine is at 10 kilopascal. So corresponding there, the enthalpy of H3 will be, we know that quality is 90%, so X is 0.9, and the saturated liquid and latent heat there is 191.83 and 2392.8. So H3 comes out to be 2345.4 kilojoule per kg. So applying a control volume across the turbine gives you work as mass into H2 minus H3. So mass flow rate at 2 is your work generated by the turbine, which is 1 megawatt, which is 1000 kilowatt, divided by the change in enthalpy, which is in kilojoules. So that's why we have written it in kilowatts. So that gives you mass flow rate at state 2, which is the mass flow rate entering the turbine is 2.543 kilograms per second. So that, and in the mass flash chamber, your flow rate ratio is M2 by M1 is 0.07439. So from there we can find out the mass flow rate coming into the flash chamber, M1, which comes out to be 123075 kg per hour. So this is the amount of mass flow rate of the geothermal water which has to be taken for generating 1 megawatt of power. So next question, we have a 200-liter tank which initially contains water at 100 kilopascal and a quality of 1%. So heat is transferred to the water, thereby raising its pressure and temperature. At a pressure of 2 megapascal, a safety valve opens and saturated vapor at 2 megapascal flows out. The process continues maintaining 2 megapascal inside the quality until the quality of in the tank is 90% and then stops. Determine the mass flow rate, mass total mass of water that flowed out of the tank and the total heat transfer. So what we have is, we have a tank, you are heating it, that contain 200 liters volume, tank with 100 kilopascal pressure, and the quality is 1% initially. So you are heating it such that the water now evaporates and vapor forms, and the pressure in that process is increasing to 2 megapascal. So this is like a boiler what you have. Then you have the inside pressure to be 2 megapascal. So the process continues, and the valve opens when once the pressure goes above 2 megapascal, and so the valve will be opened and it will maintain the pressure to be at 2 megapascal. At this point, you are stopping when your tank quality in the tank is 90%, and then it stops. So determine the total mass of water that will flow out and what is the heat transfer. So initially it will be a constant volume process till it reaches a pressure of 2 megapascal, and then there is a constant pressure process where mass is escaping and the pressure is remaining constant. So we'll see how to solve this. So first, initially this is a constant volume and a closed system, since the pressure is rising to megapascal and there is no mass transfer which is happening. So initially it is like a closed system. So applying energy balance for this. So initially M3 minus M1 equals, or we can straight away calculate what is the process happening between state 1 to 3. So applying in mass balance, we get M3 minus M1 equals the mass which is exited. So and the energy equation is the change in internal energy of the system equals the enthalpy change and similarly the heat and work interactions. So it's get minus MEHE plus Q13. So at state 1 initially you have 1% vapor. So the specific volume at that state is Vf plus x1 into Vfg. So substituting the values for initially 100 kilopascal, what we get is V1 to be 0.01797 meter cube per kg, And similarly, internal energy at state 1 is 438.22 kilojoule per kg. So the mass at state 1 comes out to be 11.13 kilograms. At state 3, when the pressure reaches 2 megapascal, the specific volume at this state for 2 megapascal is, and the quality is 0.9. In substituting, we get specific volume to be 0.8978 meter cube per kg, and U3, the specific internal energy at state 3 is 2430.88 kilojoule per kg, and the mass at state 3 will be, because the volume will remain same, 0.2 meter cube divided by specific volume, which comes out to be 2.23 kilograms. So substituting that in the above expression, we can find out how much mass has escaped, which comes out to be 8.9 kilograms of water which has escaped as steam, and the exit state pressure will be at saturated vapor, which is going out at 2 megapascal. So the saturated vapor at 2 megapascal is 2799.51 kilojoule per kg. So substituting this in the above expression for energy balance, we get Q13, the total heat supplied between state 1 and 3 is the change in internal energy plus the energy carried by the steam. So the final internal energy is 2.23 into 2430.8, and the initial internal energy was 11.13, which is the mass initially, into 438.22, which is the initial internal energy, plus 8.90 is the mass which is exiting the system, multiplied by the enthalpy of the gas carried out, is 2799.51. That gives you Q to be 25459 kilojoule or 25.46 megajoules. So that is the amount of heat which has to be supplied to reach the state 3. So in this, what we did is we applied two equations. So one is the mass balance and another is the energy balance, and to find out masses, since the volume is known and the initial and final conditions of the contents inside the cylinder is known, so we estimated the specific volume. Using specific volume and the volume of the cylinder, we estimated the masses inside the cylinder. So at state 1 it contains some mass, and state 3 it contains some mass. The difference between the mass will be the mass which has escaped, and then using this masses and the energy of the system, we substituted this in the energy balance, and then we estimated what is the heat transfer which is happening. So we got 8.90 kg of steam which is escaping the cylinder, and then the heat which has to be supplied is to be 25.46 megajoules. So this is an extension to what we did in the previous case. So previously we just had the boiler, and which was regulated by the pressure safety valve. So now whatever steam is now coming out from the valve is now driving a turbine. So that's the problem here. So we have a steam engine based on a turbine is shown as shown in figure. So the boiler tank has a volume of 100 liters and initially contains saturated liquid with a very small amount of vapor at 100 kilopascal. So just like the previous case. So heat is now added by the burner, and the pressure regulator does not open before the boiler pressure reaches 700 kilopascal. So the pressure is regulated by the valve, see, just like the previous case, which then keeps it constant. The saturated vapor enters the turbine at 700 kilopascal and is discharged to the atmosphere at a saturated vapor of 100 kilopascal. So the burner is turned off when no more liquid is present in the boiler. Find the total turbine work and the total heat transfer to the boiler for this process. So what we need to find out is once all liquid has evaporated, so there is no liquid which is present in the tank, so all are vapor. At that point, the burner is stopped. So eventually what it means is when all the liquid is evaporated and is driven by the in the turbine, so what will be the work which is generated and how much heat it will consume. So just like previous case, we will apply a separate control volumes for boiler and turbine, and for turbine so first is for boiler we will apply the same expression for mass flow balance and the energy balance. So you get M2 minus M1 is minus Me, and similarly M2 U2 minus M1 U1 gives you the heat transfer minus MEHE is the enthalpy carried by the steam going out. So from steam table for 100 kilopascal you get specific volume to be 0.01043 and U1 is 417.36 kilojoule per kg. So initially the mass contained in the cylinder is for 100 liters is 0.1 divided by the specific volume 0.001043 gives you 95.877 kilograms. So that is the amount of water which is contained in the cylinder. At state 2, this whole cylinder is emptied of liquid and there is only saturated vapor which is present in the tank, and this is at a pressure of 700 kilopascal because the pressure is maintained by the valve at the exit. So liquid whatever is now generated is everything is at 700 kilopascal. So at the end of the process when all the liquid has evaporated, so this is at 700 kilopascal saturated vapor, fully contained saturated vapor in the 100 liters volume. So saturated vapor specific volume corresponding to 700 kilopascal comes out to be 0.2729 meter cube per kg, and similarly the internal energy is 2572.5 kilojoules per kg. So the mass comes out to be the volume divided by specific volume, which is 0.1 divided by 0.2729 gives you 0.366 kilograms, and exit state is 700 kilopascal. The exit enthalpy comes out to be 2763.5 kilojoule per kg. So that is the saturated vapor enthalpy corresponding to 700 kilopascal, which is the steam which is coming out of the boiler. The turbine exit temperature is given to be 100 kilopascal. So exit state is 100 kilopascal. So the enthalpy corresponding to 100 kilopascal is 2675.5 kilojoule per kg. So the amount of mass which is going through the turbine is 95.511 kilojoule per kg, and the heat which is transferred is, applying the energy balance here, we get 0.366 is the final mass into the final internal energy minus initial mass into initial internal energy is 95.87 into 417.36 plus the mass which is exiting, which is 95.511 into the enthalpy of the saturated vapor. So that gives you Q to be 224.9 megajoules, and the turbine work will be mass which is exiting, the total mass into the change in enthalpy, which is 2763.5 minus 2675.5, it gives you 8405 kilojoules or 8.4 megajoules. See, so this says that the 224.9 megajoules of heat is required to get 8.4 megajoules of work. So it's the final problem for today. So what we have here is a mass loaded piston cylinder shown in figure containing air at 300 kilopascal and 17 degrees Celsius with a volume of 0.25 meter cube. So while at the stops, your volume is 1 meter cube. So initially the volume occupied is 0.25 meter cube. So once it expands at the stop, it reaches a volume of 1 meter cube. So an air line which contains pressure at 500 kilopascal and 600 Kelvin is connected by a valve to this piston cylinder arrangement, is now opened, and the final pressure inside reaches 400 kilopascal. At that point your temperature is 350 Kelvin. So we need to find out for the air that enters, the work and heat transfer. So what we have is initially the air is at 300 kilopascal and 17 degrees Celsius and volume is given. So that is connected to a air pipeline which is at pressure of 500 kilopascal. So we are opening the valve till the air inside the cylinder reaches 400 kilopascal. So we'll find out how much work and heat is transferred and how much air enters. So just like previous case, we'll write the mass balance and energy balance. So mass balance is m2 minus m1 is the mass which is coming in. And similarly, energy equation is m2 u2 minus m1 u1 equals mass which is coming in and the enthalpy which it carries plus the energy transfer q minus w. So at state 1 initially we know pressure, temperature and volume. So we can estimate the, for air, we can estimate what is the mass occupied. So that comes out to be 300 into 0.25 divided by your gas constant 287 into temperature 290.2. So it comes out to be 0.90 kilograms. And at state 2, similarly at the end of the process, your pressure is 400 kilopascal and temperature is 350 Kelvin, and we know that the volume reaches the stop and it is at 1 meter cube. So the mass at that point is 3.98 kilograms. So with this we can estimate now what is the mass which has entered the piston cylinder arrangement. So that is the final mass minus the initial mass, which is 3.982 minus 0.9, which comes out to be 3.082 kilograms. So the work which happened, so initially there will be constant pressure process and then constant volume once it reaches the stop. the volume will remain constant. So during the constant volume process, your pressure has remained same, and so P1 is V2 minus V1, and that is the pressure applied by the cylinder, which is 300, because that is balanced by the other pressures. So that will be 300 into the change in volume, so 1 minus 0.25, which comes out to be 225 kilojoule. So that is the work done by the piston cylinder arrangement. And then applying the energy equation, we get the heat transfer plus the energy which is going out equals the change in energy plus the work done. So substituting all the expressions, we get the heat transfer to be minus 819.2 kilojoules. So that is the amount of heat which is released from the cylinder, because initially this is at 17 degrees Celsius, and at the final point it reaches 350 degrees Celsius, because the air which is coming in, that is coming at 600 Kelvin. So that is around 325, say 327 degrees Celsius of temperature air which is going inside the piston arrangement. So that raises the temperature of the content inside, and that's why heat transfer is happening. So initially what happens is, at any point initially at the piston there is the atmospheric pressure which is acting, and similarly the piston mass which is acting on the air, and that is balanced by the pressure inside the cylinder, the air pressure inside the cylinder, which is 300 kilopascal. So this balances both the atmospheric pressure and the pressure exerted by the piston cylinder. So that gives you 300 kilopascal. So when the air initially enters and the piston starts moving, your volume is expanding, but the pressure is again at any point is balanced by these two forces, the atmospheric pressure which exerts the force, and similarly the mass of the piston which is exerting. So that is balanced by this air. So it will always be at 300 kilopascal until it reaches the stops. At that point, then additional mass which is entering the system will raise the pressure inside the cylinder. So till it reaches the stop, you have a pressure of 300 kilopascal. So here this whatever is work done by the pressure of the air, it is consumed by the cylinder, the piston and the atmosphere. So you have the system and surrounding. Only the system is our air. So the air, the work done is 300 into the delta V, which is 1 meter cube minus the 0.25 meter cube. So that is the work which is we are getting out of the air, and that will be balanced by the other forces. And then that raises the pressure, and in the process there is heat transfer, and that's what we did. So what we did is initially we estimated what is the mass contained in the cylinder, and then at state 2 again we know pressure and temperature. We found out what is the mass at state 2, and then we found out the difference in mass, which will give you how much mass is entering the cylinder. And we know the pressure and temperature of air from the air pipeline, so that we assume that that remains same. So the enthalpy of the air entering the cylinder will remain same. And that we found out using MCP delta T. And similarly we found out corresponding to the temperature at the initial and final, we found out the change in internal energy, and work done which we calculated, so P delta V. Using all these quantities we can estimate the only unknown here will be the heat transfer, and that comes out to be 819.2 kilojoules. With this, we have finished some problems on open system applied to first law applied to open systems. So we saw problems using applying steady flow energy equations. So how that can be applied to a component, or if you have multiple components, how do you apply to those? So we take into account individual components and then solve. And just like the problem in the power generation using a geothermal case, so you had flash operator and then work which is generating. So similarly, we apply control volume in each of the processes, so that can be done. And then in an unsteady case, the crucial thing is to apply both mass balance as well as an energy balance. So uh, the energy equation will be similar to steady flow energy equation. So the only additional term is the energy accumulated, or the energy change in the control volume. So that is given by the change in the internal energy. So we usually, whatever content inside the control volume, we assume that the kinetic energy and potential energy are negligible. So that ultimately turns out to be the change in the internal energy of the system. So the change in internal energy is then the rest of it is the steady flow energy equation terms. So those are the two equations which we solve for a unsteady analysis. So we saw some problems on unsteady as well, and some problems on steady flow energy equation. So the next week we will also look at some more problems on this, and also some problems on entropies and second law in the next weeks. So with this I'll finish for today. So I have completed what questions I have prepared for today. So with this I'll end the session for today. Thank you. See you next week. So next week we'll see some more problems on similar or a little bit more tougher problems. Thank you. End the session.